Hi, Eric Archer here from Texas Instruments, and today Craig Beals, a chemistry teacher, is going to take us through the concept of the mole, except he's got a very interesting way to do it. Craig, can you tell us a little bit about that?
Well, we're going to go through the basics of what the mole is and Avogadro's number, and then at the end, we're going to make some Oobleck. And Oobleck is the super magical non-Newtonian fluid that if you've never made it before, you need to make it. You have to do this for yourself because it's just one of the most curious things that you can play with. But we're going to use the mole concept to share the recipe for the perfect Oobleck.
It sounds like a lot of fun. Oobleck is a funny word, so I'm hoping it lives up to its name.
It does. I think it comes straight from Dr. Seuss.
Yeah, awesome.
The mole. In basic chemistry, this is one of the fundamentals, is the mole. And people always think of the fuzzy little critter, the mole, when we talk about the mole. But in chemistry, it is something far different and incredibly important to being able to master chemistry, or really even to understand it. So what is a mole in chemistry? A mole is a unit of measurement of quantities of very small particles. In other words, if we're trying to figure out how many atoms or molecules or formula units of something are in something, we need the mole to be able to do that. Now, let me make an analogy here. Let's start with a mole in chemistry is not the fuzzy little critter. What is it? The mole is a unit of measurement of quantities of very small particles. In chemistry, we deal with things like atoms and molecules, which you can't see, but you still have to be able to measure them. So I'm going to make an analogy here with a dozen, because most of us are familiar with what a dozen is. Let's say a dozen eggs is 12 eggs. We're all pretty familiar with that. Well, the analogy here is a mole of eggs is 6.02 times 10 to the 23rd eggs. So notice, we're all familiar with a dozen. A dozen eggs is 12 eggs. A mole of eggs is 6.02 times 10 to the 23rd eggs. That's a lot of eggs. Maybe it's something like atoms. A dozen atoms is 12 atoms. A mole of atoms is 6.02 times 10 to the 23rd atoms. Now, why do we need to know that? Well, let's get there and find out. The number that you just saw on the last screen where we were talking about a mole is not actually the mole number, it's Avogadro's number, okay? Avogadro's number is 6.02 times 10 to the 23rd. It's a number you need to memorize in chemistry because you'll be using it all the time. And it's named after a gentleman named Avogadro, who was, I believe, an Italian scientist many years ago. This is a massive number. I added all the zeros to the number here because, well, I wanted you to be able to see what it looks like. Why is that number so big? It's so big because atoms are so small. And you have to have a whole lot of atoms to have something big enough to be able to work with in chemistry. This number helps us with that. So a mole of something, a mole of anything, maybe it's a mole of molecules, we abbreviate molecules like this, is 6.02 times 10 to the 23rd molecules. A mole of dollar bills is 6.02 times 10 to the 23rd dollar bills. It is anything. So why do we need the mole? Well, it allows us to make conversions in chemistry. We've talked about dimensional analysis and how you do conversions. The mole is the fundamental conversion factor in chemistry. For things like how many atoms of gold are in a 1 gram gold coin? You need to have the mole to be able to answer that question. Or how many molecules of water are in a 1 milliliter drop of water? You have to have the mole, or Avogadro's number, to be able to answer that. And something that's probably a little more applicable, a common pain reliever has 325 milligrams of acetaminophen per dose. If you're making those doses, you need to know exactly how much acetaminophen you need to make to put in that dose. And this is what's happening in pharmaceuticals and in STEM careers all the time. And the mole helps us answer these questions. So Let me put up my Inspire calculator and we'll start practicing a few of these. Let's use aluminum as our first example and figure out why we really need to understand the mole. How many atoms are in 1 mole of aluminum? We have learned that in dimensional analysis, we just write down what we know. And what we know right now is that we have 1 mole of aluminum, and we need to find out how many atoms that is. So 1 mole, we abbreviate it MOL, which isn't much of an abbreviation. Get to lose 1 letter, but hey, you know, 1 letter makes a difference down the road. We need a conversion factor with moles of aluminum on the bottom, because these two need to cancel. And we can turn moles of aluminum into just about any other unit of aluminum we can think of. That's what makes it so easy. So I'm going to come over here to aluminum. Actually, in a moment I will. I'm not going to go over there quite yet. I'm going to turn it into atoms, because we learned earlier, and we'll practice more of it, that 1 mole of aluminum is how many atoms of aluminum? It's Avogadro's number, right? 6.02 times 10 to the 23rd atoms. These are going to cancel, moles, and I'm left with atoms. So now all I need to do is type this into the calculator, which of course we don't need to do that because it's just 1 times this. That means it's 6.02 times 10 to the 23rd atoms of aluminum in 1 mole of aluminum. That's going to be our universal conversion factor. Let me clear this and we'll take it 1 step further. All right. Then how many grams is 1 mole of aluminum? This is just dimensional analysis as well. So we've got 1 mole of aluminum, 1 mole of aluminum. We need a conversion factor to get rid of moles of aluminum. And I can't go directly from moles of aluminum into grams of aluminum. I mean, with Avogadro's number. Instead, I have to go over here to the periodic table. So if we find aluminum, see if I can find it, we're going to click right there, and I can see the atomic weight. Now, the atomic weight tells us something about the weight of the atom, but the great thing about this mole concept, it also tells us how many grams are in 1 mole, which means 1 mole of aluminum is equal to that number up there, 26.98 grams. So 26.98 grams of aluminum. Those cancel, and now I've just converted from grams into moles. So 26.98 grams of aluminum is 1 mole of aluminum, and I can find that right on my periodic table. What we just looked at up here with aluminum is something called the molar mass. That's the mass of 1 mole of that element. We can also use it for a compound, and I'll show you an example of that in just a little bit. But molar mass is really the most useful part of understanding the mole. Well, let's put that to work. So molar mass is the mass of 1 mole of an element or a compound. We just did the molar mass of aluminum. We clicked on aluminum in our periodic table. It told us exactly what it was. It was 26.98 grams of aluminum in 1 mole of aluminum. Notice this turns into a conversion factor that we can use in dimensional analysis. The other amazing thing about this is that 1 mole of aluminum is equivalent to 26.98 grams of aluminum. Notice we can flip-flop these conversion factors so that we can use them any way we want. I won't flip-flop them for all of them, but let's go over to oxygen. Here's oxygen. We're going to look at the molar mass of oxygen. I'm sorry, the atomic weight, which translates to the molar mass, and it's 15.99. 15.99 grams of oxygen is 1 mole of oxygen. Well, what about down here? Oxygen is a diatomic molecule, so it never really exists on its own. It exists attached to something else. What if we have O2? Now, that's a compound, that's a molecule, and we have 2 oxygens. We know that one of them was 15.99 grams of oxygen. If we have 2 of them, we just times it by 2. We come over to our calculator and we take 15.99 times 2. And we have the molar mass of O2, 31.98 grams per mole of O2. So there's molar mass. We got to take that a little bit further to understand the rest of the mole. Well, let's examine the molar mass of a much larger molecule. We have aluminum oxide, Al2O3. And what we need to do then is break this up. I do it a very specific way every single time to make sure that I don't make any mistakes. And I'm going to break it up into the parts and pieces. We have aluminum, and we have 2 of those. So you'll see me do this the same every time. Oxygen, we have 3 of them. Each aluminum, if you remember from before, had a molar mass of 26.98. So 26.98 times 2. That's what I'm showing here, but I put the numbers in. And then oxygen, there are 3 of those. And each oxygen was, let's go back here, should be 15.99. And it is. So we've got 15.99 times 3. We can go back to our calculator and put these in. So we got 26.98 times 2 equals 53.96. Okay, 53.96. Then we've got 15.99 times 3. 47.97. All we have to do then is add these up, and that will tell us the mass of that molecule, or the mass of 1 mole of that molecule. Put it in the calculator. We've got 53.96 plus 47.97. Enter, and our answer is 101.93. That's the molar mass. That's grams per mole. Circle that for aluminum oxide. One step further. And so this is my last example before we jump into the Oobleck, to show you that we can combine the moles and the dimensional analysis to solve more complex problems. And what we do for dimensional analysis never changes. It doesn't matter how complex the problem is. We just write down what we know. What we know is something that has numbers with us. So we have 4.22 times 10 to the 24th molecules, M-O-L-E-C, of Al2O3. We're trying to figure out how many grams that is. So I need a conversion factor right here, and I'm going to put molecules of I got to be careful. Let me undo here because I wrote mole. This is molecule of Al2O3. And I can turn molecules into moles. I can't turn it directly into grams. That's the reason we have moles. So moles of Al2O3. Now let's think about this, because we just did some work on these on the last slide. We found out that 1 mole is how many molecules. I'm sorry, let me take a step back. We didn't figure it out on the last slide. This is going back to Avogadro's number. 1 mole of anything is 6.02 times 10 to the 23rd of that thing, molecules of aluminum oxide. I apologize for the poor handwriting. That says 6.02 times 10 to the 23rd. These will cancel. Okay, and then I'm going to go ahead and get an answer here. I could keep going, but I'm out of room. So I'm going to get an answer here, and then I'm going to carry my conversion down here where I have some more space. We're going to plug this into the calculator. We got 4.22 times 10 to the 24th. I'm going to use the EE button. because that means times 10 to the 24th. Going to take that whole thing times 1. I guess I don't need times 1, do I? I need divided by Avogadro's number, which is 6.02 EE times 10 to the, that's what that means, 23rd. Hit enter. So there's my answer for the first part. Now notice that answer is in molecules. So I'm going to go ahead and write that out so we can keep track of it. We've got 7.01. I'm going to round that up to 7.01 because of something called significant digits. We won't worry about that right now, but that's why I'm rounding it. That's moles of Al2O3. How do I know it's moles? Because that was the only thing I had left up here. Now I'm in moles, but I want to be in grams. So I need another conversion factor right here to get rid of moles of Al2O3 and turn that into grams of Al2O3. Now I have moles and mass and moles and mass. Oh, that's the molar mass. Now we calculated the molar mass before. We said that 1 mole of Al2O3 was 101 point, let me move this, 0.93. So 101.93 grams. These will cancel. And all I need to do is type it into the calculator. I've got 7.01 times 101.93. Hit the enter. There's my answer. Do a different color, make it nice and legible. We have 714.53. Again, significant digits is a whole other conversation. So if you're wondering about those, you'll have to watch another video on that. And that's Al2O3. Here's what we did. We just figured out how many grams I would have to measure out on my balance, how much aluminum oxide I would have to set on my balance to have this many molecules of aluminum oxide, which means now you can see that we can start to actually measure the number of molecules of something using a balance, which we tend to have in the chemistry lab. So that tells me we're at the point where you can try something. So this is where you need to try the recipe for Oobleck. Oobleck is this amazing non-Newtonian fluid, and it's just made up of cornstarch and water. It is called a non-Newtonian fluid because it doesn't follow Newton's laws of viscosity. The reason is when you squeeze it, it actually becomes less or more viscous. It doesn't move. And then when you let go of that pressure, it becomes viscous and it flows very easily, kind of the opposite of what you would expect to happen. Now, I'm going to give you the recipe to make Oobleck at home, to make perfect Oobleck at home. All you're going to need is to mix 4.22 times 10 to the 24th molecules of water and 1.44 times 10 to the 23rd molecules of cornstarch. That's it. You mix them together and you have perfect Oobleck. Now, if you're wondering, wait a minute, I don't know how to do that. Actually, you do know how to do that because all you need to do is convert molecules of water into grams of water. How do you do that? That's the exact same numbers we had on the last slide. So back up the video and you'll figure out how to convert between molecules and grams. And then convert the molecules of cornstarch into grams of cornstarch and you've got the perfect recipe. Now, if you don't know how many grams of water, if that converts into milliliters, just go ahead and look that up and you can make that conversion using dimensional analysis at the end. But I highly encourage you, don't just walk away from this slide. Get out some cornstarch, get out some water, and make yourself some Oobleck. Because after all, well, that's the mole in action. Oobleck is this amazing non-Newtonian fluid, which means it doesn't follow Newton's rules for viscous substances. As we change the pressure, we change the viscosity, and some interesting things start to happen. Look at this. If we squeeze on it, it acts as a solid, but soon as we let the pressure go, it turns into a liquid. Who said chemistry couldn't be fun? That's the way it should be. Oobleck, moles, dimensional analysis, That's right.
Craig, that was awesome. Thank you so much for walking us through the concept of the mole and how to use it as a tool to understand the relationship between, the molecules of some substance and the grams, how much mass they may have, and how moles play a role in that, making that conversion easier. But the favorite part of this is Oobleck. Really cool job on that. And I wrote down the recipe, and so I'm going to give it a try at home.
Very good. Yeah, I hope everybody does.